Welcome to Atmospheric Tales, a podcast that amplifies stories and experiences related to air pollution and climate change from around the world. I'm your host Shazad Ghani, and welcome to another episode of Atmospheric Tales. Our interviewer for this episode is Dr. Stephanie Mason. Stephanie is the Research and Communications Coordinator for the PEAKS program at the Institute for Atmospheric and Earth System Research, or INAR, at the University of Helsinki. The PEAKS program is a climate, air quality, and research infrastructure initiative focused on the North Eurasian and Arctic regions. Stephanie and I are colleagues at INAR at the University of Helsinki. Our guest is a professor at the Institute for Climate and Atmospheric Science at the University of Leeds in the UK. His interests primarily lie in the boundary layer processes, with expertise in turbulent air-sea exchange and Arctic boundary layers. He has extensive experience in many aspects of field measurement, such as aircraft-based measurements, oceanographic research cruises, and surface-based campaigns. He has undertaken field work all over the world, from the central Arctic Ocean to the Weddell Sea, and from the Persian Gulf to the South China Sea. He is currently part of the Mosaic expedition, the largest polar expedition in history. The objective of this expedition is to take the closest look ever at the Arctic as the epicenter of global warming and to better understand global climate change. I'm excited to welcome our guest, Professor Ian Brooks. Welcome to the show, Ian and Stephanie.
Thank you very much, Asad. Thank you for having us. And I'm really excited to start. So, Ian, let's just get into it. Polar expeditions have been one of our fascinations, even as for the general audience, just thinking about those explorers that from the 1900s have been just venturing into those icy, barren areas, looking to chart a territory that has been previously uncharted. So they just went in with dog sleds and so on. The Mosaic is termed the largest expedition in history, and it's still part of this exploration of new places, but it is additionally dealing with a very pressing problem that we're having, which is climate change. Perhaps many of us might think that the Arctic is something that's very distant and away from us, but it's actually affecting our climate system. So we can say that whatever happens in the Arctic does not stay in the Arctic. The Mosaic is this massive expedition with a team of hundreds of researchers, and you're looking at different parts of the Arctic, from the ocean to the atmospheric component. So what are the big questions that the Mosaic is trying to answer as a whole, and why do you need such a scale?
The overarching question that Mosaic is trying to answer or to explore is that of climate change processes. The Arctic is changing very quickly. It's warming about 2 to 3 times as fast as the world as a whole. That's due to some processes that are unique to the Arctic that make it warm faster than anywhere else. And we want to be able to predict how that is going to change in future and what the impacts are on the rest of the world's climate. And for that, we need to use climate models. But those models have large uncertainty in the Arctic. Their discrepancy between different models is greater in the Arctic than it is anywhere else. And while they all show an amplified warming there, they don't capture all of the details. In particular, one of the sort of poster child for Arctic climate change is this idea of the sea ice retreating. So we get these summer minimum sea ice is now much, much less than it was even a decade ago. And that's been declining steadily for as long as we've really been measuring it, back to the late 1970s when we got first satellite measurements. The decline in sea ice is not fully captured by the climate models. So the climate change we're observing is faster than that we are seeing with the climate models. The reason for that is probably down to details of processes within those models that are parameterized in terms of the variables that the model can actually resolve. So the model grid scales for a climate model maybe 100 kilometers of grid points. And so you can't represent in things like individual ice flows or individual clouds can't be represented in the model. You have to parameterize those in terms of the variables that it can, the sort of mean variables that it can represent. The reason that we have this large uncertainty or discrepancy between different models, and the reason they don't represent the decline of sea ice in full that we've observed, is down to probably problems with these parameterizations within the model. Some of them we have a good idea of what they might be. So we know that the models don't represent clouds as well as they should. Probably there are processes that are not represented well that we aren't aware of. Some processes that may not be in there at all because we simply don't know that they're important. or we've never made measurements of them, we've never observed them. So the only way we can really get to grips with that and try and improve the model is to go and make measurements. And we know the climate system is very interlinked. There are lots of different parts of it that interact. So the atmosphere, the ocean, the sea ice, there is chemistry in both the atmosphere and ocean. There's biological processes that interact with the chemistry that then interact with things like aerosol particles in the atmosphere, which influence cloud properties, which influence the radiation budget, how much solar radiation or infrared radiation there is reaching the surface, which then affects the ice melt and so on. So all these processes are all very, very interlinked. So the only way we can really get a good handle on what is going on is if we try and measure all of these in situ. And there have been projects in the past that look at parts of the system. So there's a lot of sort of individual atmospheric science projects, maybe dedicated sea ice projects and oceanography projects. But Mosaic is probably the first time we've really brought together all of these different areas of science to try and make measurements together that are truly multidisciplinary and to try and capture the interactions between all these different processes. That's the reason it needs to be so big, why we need hundreds of different researchers, because you need this huge range of expertise. The other reason it's perhaps logistically a big challenge is that if you want to measure the climate, understand climate processes, you need to understand that for the whole year. And that's a real challenge in the Arctic. Most Arctic field campaigns are summer campaigns. They go up in maybe May, June, will come out in October, maybe early November, because that's the only time of year that it's relatively easy to travel there, to get an icebreaker to sail through the sea ice. So Mosaic is freezing in for a full year to try and capture the winter processes, which we have very, very few measurements of. The last time anything remotely comparable to Mosaic was tried was back in the late 90s with the Sheba campaign. That was a US project that froze an icebreaker into the sea ice on the Alaskan side of the Arctic. And as a measure of the sort of change that we've seen in the Arctic, where they froze that icebreaker in 1997, that region is free of sea ice every summer now. You could not do that campaign in the same place.
You've mentioned now about being frozen into the ice. Can you let us in a little bit more on how you were, because now the flow broke, but how you were locked into the flow and what this means and how it drifted? Because the name itself, the Drifting Observatory, you were drifting with this flow.
Yeah, so the reason we wanted to drift is partly a practical reason. A lot of the measurements we want to make from the oceanographic side and from the atmospheric side, we want to get away from the ship, because the ship is its own little world. It affects the air and the ocean around it. And to get undisturbed measurements, we need to get away from the ship. So we need to put instruments out on the ice. Then there are measurements of the ice itself, which obviously need to be done out there, and measurements of things like the biology on the underside of the ice, where you need to get out and make ice samples. So from that perspective, we want to be able to work on the ice. And the easiest way of doing that, if you need to put some infrastructure out, is that you want to stick with the same piece of ice and just drift with it. The other reason for that, as a purely scientific one, is that when trying to capture these processes over the course of a year, you want to stick with the same region, the same bit of ice, so that you can follow its evolution over time. That gives us the sort of scientific and practical reasons. When we went up there in September last year, we sailed on I think it was the 25th of September from Tromsø. We went up into the ice, and we're looking for a large, stable ice flow that would make a good home. We could put a lot of instrumentation out on it. If it's stable, then we have a good chance of the instrumentation surviving the year. If it's unstable, then there's a serious risk that we're going to lose expensive pieces of kit. Never a good thing. And so we went around, we were using satellite imagery to try and identify potentially suitable flows, and we then took the ship to them, or sometimes they took a helicopter flight out so they could examine flows within a few tens of kilometers of the ship. We actually had quite a challenge to find a flow that was large enough, thick enough, and stable enough to work with. Most of the ice there at that time is very thin. We were at the end of the summer, so it was the period of the minimum ice extent, and a lot of the ice there was only maybe 30 centimeters thick. It was very thin, very weak, not at all suitable to put a camp on. Eventually, we did find a flow. It was maybe a kilometer or so across, varied in thickness from maybe a meter up to, or maybe a little less than a meter in its thinner places, up to a couple of 3 meters where there was ridging and thicker ice. And once we determined that was where we were going to stay, then they found a good spot to moor the ship to, put out securing lines to tie the ship up to the floe. And from that point, the ship and the floe were just going to drift together. Hopefully, it was hoped for a full year. In the end, it hasn't worked out quite like that, but you basically get what you're given out there. So you have to work with whatever happens. Once we'd got that floe, then we come with the challenge of setting up instrumentation on that.
When you're actually out there, you have this floe and you're setting up your camp. What's it like to be standing on that floe? This very expansive area where there's nothing but the ice and the wind is coming. And how does it sound? What kind of things can you see? And then the winter sets in, it's complete darkness. Can you tell us a little bit about how it was?
Being out on the sea ice, working on it, is always great. It's really exciting stuff to do. In many ways, it's very bleak. I mean, you're out on the sea ice, it's relatively flat. One bit looks much like another bit with occasional ridges for variation, but it's actually really beautiful, especially during the summer when it's well lit. You have 24 hours of daylight. The range of blues is stunningly beautiful, and it's great to get a little bit away from the ship, where it can be really quiet. The time we were setting up was sort of towards the end of the summer. We had initially, I think, for about the first week of setup, maybe first 2 weeks, we had reasonable daylight, but we had a sunset every evening. And then towards the end of that time, basically the sunset, that was the last we saw of sunlight for months. And we have a couple of 3 weeks or so where it's really just twilight all the time. So you've got this beautiful permanent sort of late sunset lighting in the sky, which sort of varies a little bit over the 24 hours of the day, but it's basically twilight all the time. And slowly all the colors become darker and darker blues and purples, tinged a bit with that red in the sky. And that's really beautiful. Most of the time during the setup here, we had reasonably good weather conditions. We'd occasionally get fog. That's always a problem. When the fog comes in, can be quite beautiful in the summer, that you've just got these shifting bluey grays, but it's a safety issue, because once the fog comes in and you can't see very far, then you can't see any potential hazards. The big one being polar bears, of course. You want to be able to see if a polar bear is coming up towards you. They move really quietly. You would hope to see them before you would hear them. Although we're out on the ice and it's usually pretty quiet when you get away from the ship, it's not totally silent. Sound travels quite well. So there's always this sort of background hum of the ship, because that's got its engines running just for generating electricity and heating all the time. So it's just got sort of auxiliary engines running, and there may be cranes running, and then people around on skidoos perhaps moving stuff while we're setting up. So there's always a little bit of noise. Some of my colleagues who were dealing with some remote meteorological stations that were deployed about 15 kilometers from the ship, and they would go out to service those with a helicopter, and the helicopter would drop them off, and then it would come back and do something else, and they would be left out there miles from anybody else with no sources of sound at all. And there, one of the experienced bear guards who was out there with them said it was quiet enough that you would be able to hear the bear coming as its feet crunched into the snow. You have to always be aware. So whenever we're working out on the ice, you always have to have a dedicated bear guard with every group. So somebody is there, they have a rifle, they've got a set of binoculars, flare gun to try and scare any bears off with, and their job is just to keep watch. They're not allowed to go and help with other work. Even if it's one of the scientists who's volunteered for bear guard duty, you can't go and help with a science activity, because the tendency is you'll get distracted, you'll get occupied and sort of focused on the science and forget to keep watch. So always have a bear guard. I did quite a bit of bear guarding on Mosaic. I really enjoyed doing that, because it's a chance to sort of get away from everybody. You can go and stand out on a ridge where there's a good view and feel really isolated in a way, and you've got this amazing feeling of isolation and just these sort of views out across the ice. This was my first time doing a winter campaign. I've done 4 previous cruises up into the Central Arctic during summer, but this is the first time that I was there over winter and experienced that complete darkness, which was really different experience that you can't. In the summer, you can see a lot of the time for all the way to the horizon, tens of miles. The visibility is usually fantastically good, or if you've got fog, very, very poor. There isn't really much in that intermediate. In the winter, it's dark, you can't see sometimes more than 50 to 100 meters. And near the ship, there's usually enough light to see further. But if you were out with one of the more distant sites, you would have high-powered headlamp to keep watch, although often the sort of reflection off the snow and ridges would dazzle you. I tended to keep the light off and let my eyes become acclimatized to the dark. But that is really special experience. It is great being out almost on your own, away from other people, and just sort of being able to just experience that isolation. And that's something I really, really enjoyed.
Right. It's really impressive to hear the things that come with doing science in the Arctic. It's not just a group of scientists with a little test tube. It's really impressive what you have to do to be able to do your science. And now you're talking about this helicopter. You mentioned there was a helicopter, and actually there were balloons, drones, helicopters, in addition to, other more stationary instruments as well. And then you have names like METCT and Miss Piggy and the Beluga. Can you tell us from your atmospheric team, because you're part of the atmospheric team, if you could take a snapshot standing on that floe, what are we able to see from the ground up? So from the ice interface between the ocean and the atmosphere, what processes?
All the stuff that we're studying is almost all of it is invisible from an atmospheric science perspective. So this is where we need all these different instruments. Starting at the surface, one of the important things that we're looking at, and one of my areas of research, is the turbulent interaction between the atmosphere and the surface. So this is the friction that the wind experiences blowing over a rough surface that generates chaotic, turbulent mixing, and it transfers momentum from the atmosphere to the surface, and that's going to push the ice around effectively. So this moves the ice around on the surface of the ocean. Ultimately, it also generates near surface currents and mixing within the ocean. And from the perspective of the ice, that stress, the wind stress on the ice surface, is what moves it around en masse. So it's partly why the ice drift is coming across the pole we started out on the sort of Russian side of the North Pole. The ship and the ice floe drifted right across near the pole and over towards the Fram Strait. And that drift is largely driven by, ultimately, the wind and the wind stress on the surface. It also can cause stresses in the ice, so it can cause it to fracture, cracks to appear in the ice, and they can open up to expose water, or it can push the ice back together, and then it can buckle and form ridges. So the wind stress on the surface is responsible for a lot of the dynamics in the ice itself. Then as we move up through the atmosphere, the lowest few hundred meters is dominated by turbulent mixing. That is trying to mix everything out to make the properties in that lowest few hundred meters relatively uniform. And that's competing with things like long wave radiative cooling of the surface, so the loss of heat by infrared radiation from the surface, which is trying to stabilize the atmosphere. That will lead to stable stratification, which suppresses turbulent mixing. Then both those sort of radiative processes and the turbulence interact with low-level clouds. So typically during much of the year, the Arctic has a lot of cloud cover at an altitude of, say, between a few hundred meters and a kilometer. So there's usually stratiform cloud in this layer. That cloud is a strong control, the strongest control on the surface energy budget, because it has a big impact on radiation. It will, during the summer, act to reduce the amount of solar radiation that reaches the surface, but it also emits infrared radiation and acts as a source of warming at the surface. Now, from a climate perspective, over most of the globe, these low-level clouds act as a cooling influence on the surface. They reflect more solar radiation than they emit infrared. But in the Arctic, even during the summer when there's 24 hours of daylight, the strength of that sunlight isn't that strong, because the solar elevation angle is very low. It's always down towards the horizon when you're right up at the pole. And so, in fact, from almost all of the year, the infrared radiation from these low clouds has a stronger influence than the solar radiation that's blocked by the clouds. And so these low clouds act as a source of warming at the surface for probably something like 8 or 9 months of the year. The only time where the clouds reflect more solar radiation than they emit infrared is during a couple of months at the peak of summer. particularly as you get up to pole, it gets to be a longer period as you come towards the edge of the ice at slightly lower latitude, sort of down to maybe 75, 70 degrees north. But on average, over the whole of the Arctic Ocean, something like 8 to 9 months of the year, the clouds have a stronger infrared than solar impact. So they're really important for that surface energy budget. And that's one of the things that Mosaic was really trying to study, is the cloud processes and properties, because they are one of the real weak points in climate models. They're really difficult to represent well. As simple factors, these clouds are often very thin. They may only be a couple of 100 meters. And in terms of a large-scale climate model, that means you may only have 2 or 3 vertical grid points that are within the cloud. So you really can't resolve it, even in a very simple sort of sense, as just a horizontal slab of cloud within the model is very poorly resolved. So a lot of measurements were focused on the clouds, particularly from the US. They had a huge array of radars and LiDARs, remote sensing measurements. They had, probably 4 or 5 different cloud radars up on the ship. I had some LiDARs. The team from Tropos in Germany that had another LiDAR that's measuring mostly aerosol properties through the whole of the atmosphere. What we hope is that bringing all these measurements together, we'll be able to really understand the processes in the cloud, what controls them. We also need to bring in measurements of the aerosol in the atmosphere. So all these little tiny particles that are floating around that are what the cloud droplets and ice crystals form on. And the Arctic is, from an aerosol perspective, a really, really extreme environment, in that it is very, very clean in the atmospheric boundary layer in the Arctic, because there is almost always cloud. There is very frequent precipitation, mostly in terms of ice crystals or snow, and that scrubs the aerosol out of the air. It basically scrubs it clean, acts as a big filter. And whereas here in Leeds, the atmospheric aerosol concentration near the surface is probably thousands of particles per cubic centimeter. Over a clean marine ocean boundary layer, concentrations are probably a few hundred particles, typically per cubic centimeter. You get up into the Arctic and you can have, I think the average concentration of particles is something like 20 or 30 particles per cubic centimeter. And there are often times when that concentration drops down below 1 particle per cubic centimeter. So it is almost nothing there to measure. And that's something, again, is really difficult to handle within the models, where a lot of the models just prescribe a nominal cloud condensation nuclei concentration of something like 50 or 100 particles per cc, and that's way too high for most Arctic conditions. If you want to deal with it properly, then you need to do real interactive aerosol physics within the model, but that becomes very computationally expensive. But also, to do that properly, you need to understand all the processes that the aerosols undergo. You need to understand what their sources are, what the sinks, the loss processes are, and all of those are really uncertain. We don't really understand where the sources are, or at least the dominant sources of aerosol in the Arctic, whether they are primary particles from the surface, so particles that are ejected from open water, or maybe there's ideas that they may be sea salt particles from saline snow, which in strong winds evaporates and leaves aerosol particles behind, or whether it's long-range transport above the boundary layer that's bringing aerosol in, which then gets mixed down at the top of cloud. All of these we know happen. Also new particle formation, so from gases emitted from the surface that may then undergo chemical reactions from which particles condense out, nucleate to form new particles. We know all of these processes do happen. We don't really understand which of them are dominant and most important, or under what conditions in the Arctic. So that's a real challenge. And there was a large amount of instrumentation focused on aerosol processes, multiple different aerosol physics groups and aerosol chemistry groups working on the ship. The aerosol people will get a really fantastic data set out of that. We should keep them busy for years doing the analysis.
Yes, I have colleagues working on that right now. So it's, yeah, I hear their enthusiasm when they're coming back. And with all those instruments that you're talking about, like I mentioned, this Miss Piggy, you have a balloon, I believe, and the Beluga, it's also a balloon. You have these really cool names. By the way, who came up with these names?
I mean, the names are usually ones of convenience. I mean, I think Miss Piggy was given that name. I'm not sure if it was given the name on the cruise or if they already called it that, but that's because it's a blimp, essentially. There's a small blimp. It's red, so sort of vaguely pink colored. it's like a pig's body shape, so it got called Miss Piggy. And then the Beluga is a much bigger blimp. That was only run during the summer. That wasn't run while I was out there. And that is a convenient sort of descriptive name for it. And things like the various sites, we had Met City and Ocean City. These end up being sort of initially, I guess, nicknames for places that you need to be able to refer to places conveniently. So just calling this sort of central area of the ice floe the fortress, because it was a sort of ring of ridges that looked like it might be a fortress. And there was some area where there was a lot of distorted ice blocks that had been churned up and then carved by the wind and melted out during a bit in the summer. And somebody called that, it was like a sculpture garden. So all these names got put on the map. And it then just gives you an easy way of referring to where somebody is going or where instruments are going to be sited, that you don't have to give long, complicated description, or you can't even give GPS coordinates because we're moving with the ice is drifting. So all the coordinates keep changing. So it's handy to have these names. So Met City was where I spent most of my time. That was where most of the meteorological measurements were installed, which was about as far away from the ship as any of the measurement sites, because we wanted to keep away from the flow distortion caused by the ship and emissions of, from exhaust gases and aerosol from the ship.
And talking again about this instrumentation, when you're actually there, things can happen, and not just with the instrument. Like I said, I have colleagues, and sometimes they're happy reporting that everything's fine. Sometimes the instrument isn't working that well. But also things like when the COVID started, and then the Polarstern the ship had to make an unplanned trip to pick up researchers. So when you have to make big changes in terms of logistics, and you've built this huge camp, and you have to perhaps undo it or redo it.
Yeah.
How do you deal with that, and how does it affect your science?
There's a big impact on the science because because of COVID, they could no longer do the planned transfer of personnel with a Russian ship. And so the Polarstern had to come out. So it was away from the measurement side, away from the flow for about 3 weeks. And then you have all the decisions of, well, that's a gap in the time series for any of the people who are going out making direct samples. So the ecology team and the ice physics people who are going out and taking regular ice cores through the ice floe, which were then taken back into the lab for analysis. All of that stops for several weeks. So that's a big hole in their data set. For the oceanographers and the atmospheric scientists, we have a lot of equipment that needs mains power and very often a data connection. So, for example, I had equipment out at the Met City site, it requires mains power to run because it's quite power hungry, and it generates a lot of data. And so we need a network connection to transfer the data back to the ship for archiving. So that's major infrastructure that needs putting out in terms of power lines and network cables and such like. And when they were coming out, there was a lot of discussion. We had a big meeting with the atmospheric team that were not on the ship at the time to try and decide what we were going to do. Could we operate anything autonomously? There were a few autonomous stations scattered around, as I said, about 10, 15 kilometers from the ship. Those would stay running, so we would keep some measurements. And for a while, there was a lot of discussion as to whether we could keep some of the equipment, the core measurements at the Met City site going by having a large fuel tank for a generator out there. So we had an emergency generator because occasionally we would have to have power from the ship be cut. There's a generator out there anyway, and then, well, if we have so many barrels of fuel and sort of all hook them up in sequence, we could keep, I think they thought they could keep things going for about 13 days, maybe 15 days, something like that. But then you have to judge, well, that's fine as long as everything is secure. But if the ice flow were to have a crack go through it at that point and it was then ridged and it disrupted things, then you would have a risk of maybe tipping up a barrel of oil onto the ice. And that's something we really, really didn't want to happen. There was a huge effort put into keeping everything pristine and not polluting the environment at all. So in the end, it had to be decided that they weren't going to do that, and we would have to shut everything down. So we then had the decision, okay, we accept we're going to lose the best part of a month's worth of data. We can minimize that period if we wait until the last possible minute before shutting down and leave everything in place so we can start up as soon as the ship is back on site and the power's reconnected. But again, we have the risk of, if we do that, we may lose the equipment. The ship's going to be away for nearly a month. If the ice becomes dynamic, and we had a lot of cracks through there, and we had stuff go right through the middle of camp on more than one occasion. And so there's a real risk that you could lose equipment. And in the end, most of the equipment was brought back onto the ship. It was deemed that it was too big a risk to leave it out there. There was initial intention to leave some stuff, but then just a couple of days before the ship was due to leave, another crack went right through the middle of that camp, and they're just, okay, right, this is way too risky, we'll just pull everything back on the ship. And then once they got back on site, you have to reinstall all of that, and so it's doable. It just takes time, and that means that you're losing time when you had hoped to be getting data. So we are going to end up with a couple of big gaps in the time series of measurements that we had hoped that would be continuous. The latest, of course, is that last week the flow finally broke up entirely. It's only now a few kilometers from the edge of the ice. It broke up into fragments, and they've packed everything up and brought it back on the ship. When they do the next crew exchange in a week or two's time, the ship will head back up to somewhere close to the North Pole and start basically a whole new site for the rest of the project. That was sort of planned for, that it was expected that the ship and the flow it was moored to could get ejected through the far side of the ice, and that has drifted faster than was expected. So it was sort of hoped that it wouldn't quite get there and we'd be able to keep going for the full year. In the end, it's moved faster. That's partly perhaps because the ice has been relatively thin, but it's also been quite unusual large-scale weather conditions this year. So I think the large-scale atmospheric circulation in the Arctic over this year has tended to move the ice faster than usual. That's one of the weird things about trying to do these sort of measurements, is we make all sorts of plans on the basis of the climatology, what you expect to get in terms of conditions, and you never actually get the climatology. You always get one of the, not necessarily extremes, but something that is somewhere in that distribution of conditions. And we've had a year that is climatologically unusual, perhaps. Exactly the same happened in the Sheba campaign in 97, 98, that was a climatologically unusual year, which when you're trying to measure climate is perhaps not surprising, but it's very frustrating to keep getting extremes instead of something closer to the middle of the distribution. Maybe we need longer campaigns. We need to measure over multiple years.
Well, related again to the massive scale of this. So the Polarstern is the main ship, and you have, of course, other icebreaker ships that are coming to, for example, hand over new crew, as was one of the Russian icebreakers. You have previously done many polar research campaigns, and there have been mostly within the European Union and the US collaborations, but now you have also China, Korea, and Russia included in this one. Yep. So this is massive international campaign. To us, I guess as scientists, we're really used to working together with each other, no matter what nationality. But if you look at it from a non-scientific perspective, let's say that this would be a good example of science diplomacy. What is your view in how countries join efforts to do science together beyond borders?
I think it's a really, really good thing. From a purely practical perspective on something like Mosaic, it's absolutely essential. No single country could really undertake a project like this on their own. The resources required are too great, and the Polarstern is where all the science is being focused, but it has required, as planned, several other ships. So there were a couple of Russian icebreakers, a Swedish icebreaker, Chinese icebreaker, all of which had planned to do one of the team exchanges, most of which were also making additional measurements on the way in and out. When we first went up, the Russian ship was doing the deployment of all these remote stations. So they deployed lots of equipment in a circle of about 50-kilometer diameter all around the Polarstern. I think both the Swedish and Chinese vessels were planning to do science while they were up there to do the team exchanges. And then in terms of the science expertise, I think you need that international perspective because the scientific strengths of different countries are often different. Partly that's a historical thing, what they have worked on in the past, where they have developed strengths and expertise, and you tend to build on that. Some of that is down to where you are. Clearly, the Arctic nations, Russia, Scandinavian countries, they have a strong regional focus on the Arctic because it's on their doorstep and it affects them directly. The UK doesn't have that, but we have a strong history in sort of polar research, both Arctic and Antarctic. And there's a lot of expertise, but there are also sort of current and recent government policy priorities that drive certain areas of science where they want to invest in, what they want to support. So I don't think there would be many countries which actually had the range of expertise and the logistical capacity to undertake something like this on their own. So it's absolutely essential that we have that international collaboration. And the wider that is, I think the stronger it is. You're right. We take that for granted. It's the way we work. And doing something like a cruise like this, where you are thrown together with a bunch of people. Most of the people on the ship that I was working alongside, I didn't know before Mosaic. I had not really met them. I might have sort of been at a couple of planning meetings where they were there, but those are huge meetings with hundreds of people, and we would maybe not have really talked. So when you're put together on a ship for a couple of months with 60 other scientists, you get to know each other really, really well. And you're spending most of your time together. You build really strong personal relationships that will very often last for years or decades afterwards. And I'm still working with people that I first worked with 10, 20 years ago because we got pushed together exactly like that. Almost coincidentally ended up working alongside each other. And you find you get on well. You're a fun group of people to work with. And so you sort of naturally, when you're looking for new projects, when you're planning things, you go to the people that you know who can do the job and are good to work with. And then you look at the holes, what measurements do we need that we can't cover ourselves? And then you go looking for who could fill this hole, who would be able to do the work that we need. And so those networks keep expanding. So they are, I think, both essential and really, really productive.
Can you expand those networks beyond researchers? So, for example, you as a polar expert, when we're dealing with regulations, and now that the Arctic is opening more and we have these Arctic countries, but also observers and so on, and the regulations in the Arctic are going to affect the people there, are going to even international presence in the Arctic because of new shipping routes and so on. So are we seeing enough dialogue with the other stakeholders? And this, especially because you mentioned this ability to network and to build connections really that can take you further because you're working together. Can we apply this with working with other stakeholders?
I think we can and should. It is sometimes difficult because we very often sort of get a little bit sort of siloed into our own different communities. And it is not always easy to know who you should be talking to. And you can see that maybe some science that I'm doing, I can see would have an application or potentially some importance to some issue of policy or governance or whatever in a particular region. But finding the person that you need to talk to can be quite difficult. I've been in a couple of meetings which have been trying to drive this sort of interaction between the scientific community and getting the outputs of the science pushed through into the wider world in terms of policy, or in something like a lot of the Arctic research. A big potential stakeholder is the insurance industry for shipping, because there's going to be a lot more shipping going through the Arctic, but it's a risky place to operate. You may save a lot of money if you can take your cargo vessel across the Arctic to go between Europe and China. It'll cut 2 or 3 weeks off your transit time. That's good because it will burn a lot less fuel. So that's good for CO2 emissions. It'll be lower emissions. But if you have an accident, then the ecological damage in the Arctic could be huge. And so those sort of issues are really important. There is obvious application for a lot of the work that we're doing in terms of improving forecast of ice conditions and weather forecasts to that industry. But finding who you need to talk to is a real challenge. And the people who might be the right person to talk to don't really want dozens of individual researchers pestering them all the time for individual interactions. There needs to be a mechanism to sort of steer this through single points of contact somewhere to do that. I've found that quite a difficult thing to get a handle on, coming from the science side. It helps sometimes having established even just one contact who has an inroad into the policy side. They can then often give a lot of insight as to who you should be talking to or what areas might be of interest and how you should approach things. And that going in sort of, oh, we've got all this great exciting science and we think you'd be really interested in it, probably isn't going to actually get at you anywhere. You need to have a very specific, you have a issue that we may be able to help with sort of approach. Some of that, particularly for the Arctic perspective, is increasing. I know know in the US, a lot of the funding from, say, the National Science Foundation for work in the Arctic has a requirement that you engage with the local indigenous populations in some manner. That's, I think, a good and very positive thing. But again, it's something that can be difficult to do depending what it is that you're working on, whether there is a real transfer of information that would be useful or whether you're sort of having to almost invent something for the sake of ticking a box.
Yeah, I can definitely appreciate that as individual scientists, it'd be harder to find out who can we talk to, but really we should move towards a system that the talking to or the table is always open for us to just sit down and talk amongst each other, amongst different stakeholders. But talking about more outreach, I saw some of your etchings. You do some art of landscapes, and they're really great. Do you do any other kind of science communication?
I do a bit. So I've done in the past sort of talks to local school groups. In the UK, there's a National Science Week where they sort of focus things and they'll get groups of school children coming into the university for talks about different science areas. So I've done some of those. Some things, talks to general public. So there's a fairly wide-ranging scheme certainly across the UK, maybe other parts of the world, called the Café Scientifique, which is a sort of evening sessions, usually in either sort of small public halls or maybe a room in a pub bar where it's very, very relaxed. I've done one in Leeds, which was on Arctic stuff, actually talking there. And it's sort of about a 45-minute talk and then question and answer session. And then everybody can go and get a drink and have a chat and ask questions one-to-one. Some of that sort of stuff I do. I don't do a lot of it. I don't tend to go out looking for it because while it's fun to do, it is also quite often time-consuming.
So, for example, these etchings that you do, is that part of your art life separate?
That I consider sort of completely separate. And while it's true that a lot of those landscapes are from polar environments, I've spent time down in sort of Antarctic islands on oceanographic research cruises there. And I've drawn on a lot of that for the artwork. But I can see some people have seen it as a sort of partly an outreach activity, but I really consider it as something completely separate. For me, partly it's a relaxation, sort of an escape from work. But I'm quite happy for people who want to see it as raising awareness of these remote landscapes and the fragility of them under climate change.
Thank you very much, Ian. That has been really great listening to everything you have to say, from the science to the non-science and all the issues in the logistics of this massive, massive expedition that's the Mosaic. Thank you very much for your time.
Thank you very much for having me. It's been a lot of fun talking to you.
With that, I would like to thank our guest, Ian Brooks, and our interviewer, Stephanie Mason, for joining us on Atmospheric Tales. Please reach out to us if you would like to suggest episode topics, guests, or be an interviewer on one of our episodes. Our contact information can be found on our website, atmospherictales.com. Follow us on Twitter and Facebook to stay updated about upcoming episodes and ask questions to our upcoming guests. Thanks to all our listeners for tuning in. Make sure to subscribe and share.